Welcome to our discussion of probability. Here you'll see we're continuing to build on our foundation for statistics, especially inferential statistics. So we're taking what we know about central tendency and variability, specifically means and standard deviations, and finding how they can be useful about judging the probability or likelihood of events. And that's going to help us to make decisions about if we have a research question, whether we think it's probable that our research question or hypothesis is supported, or in fact probable that it is not supported. There's not enough evidence for it. So that is the background for why we are doing all this discussion of probability, but you can see a lot of applicable aspects of this to other parts of life too, beyond just inferential statistics. So first, here is the brief overview of what we're going to be covering. We're going to be talking about what probability is, how to use it, what it looks like, then specifically how it looks in terms of distributions. Then we can talk about how it relates to some things we've already talked about, which are proportions and percentiles. We'll even talk a little bit about the binomial distribution. Normally we're talking about continuous types of variables in terms of the probability of events, but we can also talk binomial, 1 or 0 outcomes, just yes or no things. But if we take samples, and this is looking forward to the next chapter as well, how do we look at samples of events and then map them onto a distribution? So anyway, that's going to look forward to additional inferential statistics that we're going to be using, building on all of this logic that we're covering today. So first of all, let's talk about our intro to probability. Our simple definition is, how likely is it that something is going to occur, an event, an outcome? So for example, what are the chances the Browns win? How likely am I to win the lottery? Probability of rain. Of course, the meteorology field takes a lot of jokes because all you can do is make predictions about patterns that you see in the weather that you know from your past experience or know from computer models. But of course, weather prediction is far from perfect. The probability of a weather forecast coming true is almost never 100%, but you can get close to it. So those are the things to think about in terms of probability. We live in a life based on probability judgments. How likely is it that I'm going to get this job? How likely is it that I'm going to graduate with the degree I want? How likely is it that someone is going to marry me? All those things are not guarantees, and we have to make judgments about the probability or likelihood of these things. So all we're doing is taking situations where we have to encounter a lot in our daily lives and make decisions, and then just throwing some numerical probability into it. So for our statistical definition, our probability is, we have our first new thing to consider, which is our symbol for P, the probability, and then in parentheses, whatever the outcome is. So we're going to be using this italicized lowercase p a lot coming up, and if you've looked at some of the articles we've covered or journal articles that use statistics otherwise, you're going to see tons of these p's, these probabilities, and then you want to know what is the actual probability, usually in some sort of decimal, as we'll find out. So the idea is, if we have a known population, 50 red marbles, 50 white, if you blindly draw one marble, what is the probability of red? Well, it is simply 50 red marbles out of 100 total marbles, and that 50 over 100 reduces to 50% chance, or a 0.5 chance. So in this new population, what is that logic? So for example, 90 red marbles, 10 white marbles, 90 red over 100 total gives us 9 over 10. Our probability is 0.9, or 90% chance in this population that we draw a red marble. And if you were following my logic from before, there's different ways to express probability. One way is, of course, as a percentage. Another is as a decimal. And then, of course, you can do a proportion as well. Normally, when I see a proportion, I want to reduce it into a decimal anyway, but you can see the different ways of presenting the exact same probability. So, for example, each of these numbers is telling us the exact same thing. The probability of drawing a heart. Hearts represent 1/4 or 1/4 of the whole deck. So out of the whole deck, the probability of drawing one heart or any one other of the symbols or suits in cards is also 1 out of 4 chances, or a 25% chance. So basically, here's our probability formula. We take the total number of possible outcomes. In a standard card deck, I believe that is 64 cards. And if 64 total cards are there, that means if a quarter of them or a fourth of them are hearts, that means 16 out of that 64 are hearts. And of course, we can take 16 over 64 and reduce that to 1 over 4 for our probability. So let's continue our thinking about probability here. We can also calculate probability using a frequency distribution, which we should be familiar with already. So just to restate what we've already learned, we have 5 different x values, and here's the frequency of all of those x values. What is our big N? Let's say we're dealing with a population here, big N. We need to add up these frequencies to find our n size. Add these up, our n size should be 20. So that's going to be the denominator of this next question. What is the probability of selecting a score of x equals 2? Well, we have x equals 2, this value here, and we know that the frequency is 5. There are 5 values of 2. And we take that, 5 over our total n size, 20, to give us a probability of selecting an x equals 2 of, again, 1 over 4. Now, what is the probability of selecting an x equals 5? We see that we have, of our x values that equal 5, there is only 1 in this sample of 20. So 1 out of 20 gives us a 1 out of 20 probability of selecting that one x value of 5. That's our probability, 1 of 20. Now we talk about the issue of sampling. Basically, anytime we have to make a decision and we're thinking about probability, we're dealing with, I guess I can't say anytime, but most times it is a sample, which means we have one set of information to make our decision off of. In the future, it may not be the exact same set of information that we have in the future, but all we have is our options for this one time and the information that we have to make that decision. Now, ideally, and this is in a perfect world, most times we don't have a perfection when we're doing our statistics, especially our inferential statistics, but we want to have a random sample, meaning that when we do a draw, the probability for each one is equal. Meaning, if we're having a sample of people from a class, each individual has the same chance. Or you can rephrase that as the P, or the probability, stays constant for each draw. So for example, somebody sitting at the front of the class shouldn't have a higher probability of getting called on than somebody at the back of the class. Now in reality, that might not be true. But if you want to have the best chance of the probability you want to set up, you have to set up the situation to have a random, or as close to random, draw as possible. So of course, if we think about a loaded coin, well, normally we think a coin toss, heads or tails, has a 50% probability of either heads or tails. But if it's a loaded coin, that probability is in fact not the same as we expect. So of course, that the loaded coin, if we're expecting random, it turns out the results aren't going to be random. We also have the issue of, for example, drawing marbles out of a jar. What do we do in terms of once we've made a draw? Do we keep that marble out, or do we put it back in? What we need to remember is that we need sampling with replacement. You put that marble back in. So this is to keep a random draw. This is different than picking teams, for example, shirts versus skins in basketball. Typically, there's always the one person who's left. Well, if we're doing sampling with replacement, you pick someone, and then you'd be able to pick them again. Now, of course, in real life, drawing a team is not a random selection, and we're not pretending that it is. But in terms of these kinds of outcomes, And a lot of this is theoretical. We're only doing one sample, but if we were to do another one, then we would also put the first one back in. So even if you picked one marble, shook up that jar, make sure that marble you pulled out is back in there, and so that marble you pulled out still has the same probability of being drawn the second time as it did the first time. Now let's fold in what we've talked about with relation to distributions, particularly the normal distribution. If we take the normal distribution, we can divide it up. And here we see we have a z distribution, nice and symmetrical in this case. And we see our mean is 0, population mean. And then we have our z-scores of -1, -2, all the way to +1, +2. What we can do is divide up this distribution for any corresponding z-score to represent a portion of this distribution. And we can reflect this in terms of a percentage. So for example, what is the percent chance of drawing someone with a z-score of between 0 and 1 in this population? Well, we see this chunk between 0 and +1 represents 34% of the scores. So we say that person has we can say, to be more specifically, there's a 34% chance of drawing someone with a z-score of 0 to +1 from this population. Same logic goes, a z-score of +2 or more, there is a 2.28% chance of drawing a person with a z-score of +2 or more. So now we can make a couple conclusions about this basic process. There's lots of things we can do knowing that we can divide up the normal distribution this way. So first of all, let's take this distribution and notice we have it in z units down here, but we also have the raw units here. So in this case, the raw units are for height in inches for humans. What is the probability of drawing an x greater than 80? So we see clearly this is the part of the distribution that we are concerned about with this question. Once again, if you're not familiar with these, take a little practice, but probability of getting an x score greater than 80, raw value. Well, the problem is we don't have a good way to break up this distribution in the raw units. So what we need to do is convert to z units, as we'll find out. So we can, with this information, we have a population mean, we have a population standard deviation, and we have an x value. X minus the mean, 80 minus 68 over the population standard deviation gives us a z-score of, you probably guessed it, 2. And from the previous slide, we knew what is the probability of drawing someone on the normal distribution with a z-score of 2 or greater? 2.28%. Usually it's not that easy. Why? Because a lot of times the exact value we want to look at, whether it's a raw score or a z-score, isn't the one that's clearly marked on the distribution that we were just looking at. So that's not a coincidence that we picked a value of a z-score, or that corresponds to a z-score of 2, because we just covered it on the last slide. But there's a solution, as we're going to find out now. This is why we have what's called the unit normal table. Sometimes I refer to this as the z table. This is basically taking a z distribution and looking at corresponding z values and making different conclusions about that z value. So first of all, you can see z-score of 0. We know that if you divide this distribution exactly in half at the mean, half of the distribution is going to be below that mean, half the distribution is going to be above that mean. Now let's look at a different example. We can do a proportion in the body or the tail. Now as long as it's not right in the middle, if it's on one side or the other, then we have a distribution that has been sliced in a non-symmetric way. It's uneven. And what it means is the bigger part is the body, the smaller part is the tail. So for any corresponding z-score, we can, for example, z of 0.30, we can see that 61% of these scores are in the body. That makes sense. You're going to have more than 50% in the body, the bigger part. And then we see that 0.38 are in the tail. And of course, if you add these two up, 0.62, 0.38, you get the whole distribution. It's just dividing the distribution in unequal halves. Then we also have this proportion between mean and z. So this is taking from the mean to the z-score, what is the proportion in that area of the distribution. So all that this table is really helping us do is take z-values and helping us to answer questions about slicing up this distribution in the way that best helps us answer the question that we have. So let's work through some examples. What proportion of the normal distribution corresponds to a z-score greater than 1? Greater than 1, we take our z distribution, and you might want to have the z distribution at the end of your book brought up, or a printout of the handout I'm going to have available for you. So be looking at your z table when you answer these questions. But we know that if we take a distribution and then mark off z of positive 1, well, the body is going to be everything less than 1, and the tail, the smaller part, is going to be everything greater than 1. So now we just have to look at what z-score corresponds to that. So look for the from z-score of 1 proportion in the tail, and we see that it is 0.16. And once again, think about this logically. Proportion in the tail always has to be the smaller of the values compared to proportion in the body. The body's always bigger. What proportion of the normal distribution corresponds to a z-score less than 150? Less than positive 1.5. We have to be careful with our signs here. So in this case, z-score of positive 1.5, and we're looking for all values less than that. Now we are concerned with the proportion in the body of our distribution, because most scores are going to be 1.5 or less. And we see a proportion that corresponds to that. Much greater than 50%, because we've sliced our distribution on the positive side and are concerned about the bigger body side to the left of that. We can also phrase it not in words, but in symbols and values. Z-score, probability of a z-score greater than negative 1.3. And again, we look at our z-table, find 1.3. And since it's on the negative greater than that, we are concerned with the body. So we know our probability is going to be greater than 50%. And we find it's much greater, and in fact, 0.9. And finally, the probability of a z-score that is less than 2.7. And if we think about our distribution, positive 2.7 is all the way on the right side of the distribution. So almost all the scores are going to be less than that. So we know our probability is going to be very high that we get a score less than this really high positive z value. And of course, our probability is not 100% or 1, but about as close as we're ever going to see for our purposes. So there's a few more things that we can do with the unit normal or z table. We can find the proportion of scores between two values. So for example, we can find the probability of getting a z value between z of negative 0.4 and positive 1.3. How do we do this? Well, we probably want to sketch our graph. So it's good moving forward to have some scratch paper by and actually try and write some of these out. So graph our distribution and then mark where p of negative 0.4 is, and then also mark about where z of 1.3 is. Then the question is, what do we need? Proportion in the body, proportion in the tail? That's not quite going to do it. We're actually going to need to find our mean to z. So we need to find the mean to z of 0.4. And look at this in your table, and you can find that that is 0.16. And then mean to z on the other side, mean to 1.3, we find that is 0.4. And then we add those two probabilities together to fully answer the question posed here. So once again, what is the probability of drawing a z-score between negative 0.4 and positive 1.3? We find that that is a probability of 0.56 or a 56% chance. So it's really important to make sure that you are using the table, sketching this out, and then making sure you follow how this logic is used. Now a few more applications for our basic discussion of probability so far. We can also work backwards from a given percentile to find the z-score. How does that work? What is the z-score for 85%? Well, go check our table. It doesn't list it in percents, but what if we convert that percent to 0.85? So what we need to find is proportion in the body, that column in the normal table, and find the one that gets to 0.85 and then get the z-score for that. And we find out that the z-score is 1.04. What is the z-score for 50% or 0.5? This one you should be able to guess. This is going to be a z of 0. Z of 0 is exactly at the peak of the normal distribution. And that means that 50% of the scores are on the negative side and 50% are on the positive side. Then what are the z-scores for the middle 80%? Again, sketch your graph. And 40% to the right of the mean, 40% to the left of the mean. Now we're going to have to use our mean to z in the unit normal table or z table. So mean to z for, and what's that middle 80%? Well, we've divided, if we use our mean to z, we have to take that 80% and divide it into 40% on the positive side, 40% on the negative side. So then find 40% and the corresponding z-score, and then just have the positive and negative boundaries for that. So once again, it's important to be using your table, to be sketching out the distribution, to make sure you can see how all these pieces fit together. Working from the z-score to the proportion, going backwards from the proportion to the z-score. We can also fold in, as we talked about before and showed, raw scores. Raw scores, as long as we have our mean and standard deviation, we can then convert them into z-scores. And then once we have that z-score, we can come up with any proportion or probability that we need to look for. So the key is X value or raw score is not useful for our unit normal or z table. Call it a z table because you need a z score. But as long as you have the raw value, think about our z score formula. If we have the raw or X value and we have the population mean and the population standard deviation, we can then calculate our z score, and then from that z score find any proportion or probability that we have a question about. So for an applied example, take the IQ distribution. typically a mean of 100, standard deviation of 15. What is the probability of selecting an individual with an IQ above 118? So already above the mean, what's the probability of selecting someone more than a standard deviation above the mean? So first of all, we have to calculate our z-score, and just looking at these numbers, if our standard deviation is 15 and our raw score is 118, we know it's going to be just a little bit over 1. But we have to convert to the exact z-score, so we need to use our z formula, which means, again, our raw score, subtract from that our population mean, and then divide that by our population standard deviation. And of course we do, as we worked out through logic above, get a z-score that is just a little bit above 1. Now we need to find what is the proportion in the tail, because that's the smaller chunk of this z-score above the mean. In fact, z-score of 1.2, positive 1.2, what's the probability of getting a z-score higher than that? We need the proportion in the tail. Now we can have a little bit more complicated question. How would you approach the probability of selecting an individual with IQ between 70 and 121? Well, think about it. In this case, sketch our distribution first of all, and then we would need the mean to z probability between the mean and 70. And then we would need the probability of the mean to z of 121. And of course, first of all, we'd have to convert 70 into a z-score and 121 into a z-score. And then we just add up our two probabilities from each side of the mean, and then we come up with our answer to this question. What is the probability of an individual IQ between 70 and 121? And as you can imagine, 70 is 2 standard deviations below the mean. 121 is 1.5 standard deviations above the mean. Those boundaries have the big hump of the distribution in the middle, so our probability, we know, is going to be pretty high of selecting an individual between this range. Another way we can think about the normal distribution is sometimes we have values that we happen to see maybe more often than others, and this will come up with other types of distributions that we talk about in the future. But if we take the normal distribution and then we divide it into quartiles, we see that the middle 25% or the middle 50%, 25% above and below the mean, so what I'm referring to, of course, is this chunk here, contains most of the scores because that contains the peak of the distribution. We see that only 25% are in the upper quarter and another 25% in the lower quarter. And we know exactly the cutoff values, negative and positive z-score of 0.67. So that's just something that may come in handy in the future, but if you're not sure about it, you can also always just look it up on your normal table. So for example, if we wanted to find the middle quartile, you can just do mean to z, right? Or if you wanted to find the z, again, same thing for this. What is the proportion in the tail of 25%? You would get the z-score of 0.67. So different places on the table to find some of these same values. Now finally, we're just going to maybe go in a little bit of a theoretical direction, so bear with me here. Now what we were talking about was usually one sample, what's the probability of one outcome. In this case though, and it was with continuous variables, so for example, the z-scores could range from 0 to positive and negative, technically infinity, so continuous scores on the z distribution. However, you can apply some similar logic to even binomial or two outcome, yes, no, either or outcomes. So for example, with coin flips, either it's a yes or a no. There's not a high tails or a low tails, it's just tails or not tails, right? But what you can do is sort of stack up samples on top of each other. So instead of just one coin flip, we're doing samples of, for example, in this case, 4 coin flips, or even 6 coin flips. And of course, 4, there's the option of no heads, or yeah, no heads, 1 head, 2 head, 3 head, 4 heads. And of course, most of the time with 4 coin flips, you're going to get 2 heads and 2 tails, right? And we see the probability on this axis as well. Now, what happens if we expand the size of the samples? More coin flips. Well, now in this case, we have 6 coin flips. Notice what's happening here. This is starting to look like a normal distribution already. Now, it's a lot more work instead of just taking one draw of a continuous variable from a population. Here, we're going to have a whole bunch of samples. Each of these blocks represents the outcome of flipping that coin 6 times. So chances are you wouldn't even set up a distribution this way by actually doing those coin flips. You do a computer simulation. But what we can see is that we can see probability even has sort of a normal distribution, even with binomial or yes-no events. So that's going to come into play as well for some particular cases where we want to think about our probability game that we're setting up, that we're normally using with continuous variables. You can even have a little workaround or cheat if we only have binomial or yes-no outcomes. So as we look ahead to inferential statistics, there's a bunch of things to keep in mind that we'll be coming back to from this chapter. First of all, we can see that if we take, for example, a distribution and we want to say the middle 95%, what is the probability that we get something in the outer 5%? And of course, it would be not 5% for this whole thing. We have to take that total 5% and divide it by 2. 0.25% here, 0.25% here. And we see this z-score of positive and negative 1.96. A lot of times in research, you're going to see kind of this thinking. Probability of less than 0.5 that a result is not to be trusted, which means, well, 0.5 or 0.05, excuse me, probability of 0.05 that we don't trust a result, which means the other non-0.05, we actually do have pretty good trust in it. So essentially, that's going to be one of the common cutoffs that we use when we make decisions about probability. Is the probability a 0.05 or less that this extreme outcome was random, and this z of plus or minus 1.96 is something we're going to see in the future because of that reason. So of course, what do we make of an extreme score? How do we decide when it's an extreme score? Usually something more than 2 standard deviations above or below the mean, we start to think as very different from the average scores in that distribution. And maybe we've actually set up a hypothesis test to do that, to say, well, we are comparing, for example, an experimental group's performance, and what are we comparing it to? The control group. And we take our experimental group performance and put it on the distribution of control group. And if the experimental group is really different, when we stick that mean onto the control distribution, it's going to fall. If the experimental treatment is really working, it's going to fall in one of these extreme values, and that helps us to conclude that, oh, that's probably not a random thing that happened, is that experimental mean is much higher than the mean of the control group. And we have to have some sort of standard going in to say, well, we're going to make the conclusion that the experimental treatment is working, is, in this case, a big name, significantly higher than the control average if it goes higher than this score of z of 0.196, or at the same time if it's lower than z of minus 1.96. So this is, in this picture, the logic of what we're building up in the next couple chapters as well, and that we're going to continue with with some exceptions of why we can't use this distribution in the future, but we're thinking about it with z-scores now. We'll be using t and other ones in the future, but this is the basic logic that we're setting up for basically the rest of the semester. So if we have an intro psych class that has 9 freshman males, 15 freshman females, 8 sophomore males, 12 sophomore females, probability of selecting a male from this group. Well, we need the total potential outcomes. How many people are there to select from? And we find that if we add all these together, we get 44. So we already know what the answer has to be, but then out of those 44, what's the probability of selecting the males? 9 freshman males plus 8 sophomore males, we get 17 out of 44 as our probability here. All right, vertical line is drawn through a normal distribution at just above the mean at z of positive 0.25. Now we've taken our distribution and cut it in two. The smaller section corresponds to what of the whole distribution? Well, we know the smaller section, those values above 0.25, has to be the tail. So we can actually look at this in our unit normal table. We know that it has to be a probability in the tail lower than 0.5, but since the z-score isn't really that much above 0, that probability is not going to be super tiny. So in this case, if we look at our table, we should find that this z-score corresponds to 0.4 proportion in the tail. Now, we have a normal distribution with a mean of 40 and a standard deviation of 4. What is the probability of sampling an individual with a score greater than 46? Well, what do we have to do first? First of all, we might want to draw our distribution, and we can put our mean of 40 and our x value of 46 and put in the value or shade in the part of the distribution greater than 46. But we're working with raw scores. We have to get a z-score. Okay, so let's take our z-score formula, and we take our raw score, 46, minus our population mean, which is 6, over our population standard deviation, 4. 6 divided by 4. What does that give us? It gives us a z-score of 1.5. And then we can go to our table and see the score of z of 1.5 and then the proportion in the tail of z of 1.5 because we're doing greater than this value above the mean. And then you can find the value there. I don't have the table right in front of me right now, but we know it's likely to be one of these greater than 1.5 z-score, one of these smaller probability values. As I mentioned before, we might see this before. What is the two cutoffs above and below the mean for the middle 50%? And if you remembered or want to go back, there was a distribution for quartiles of a distribution that showed the plus and minus 0.67. And finally, for a normal distribution, what is the proportion in the tail beyond or lesser than a score of negative 1.5? So we can sketch our distribution, put our negative 1.5 z in there, and less than that, shade in that part of the distribution. And we're going to see the probability of that is not very good, or not very high, I should say. Of course, the probability can't be negative, so that probability for that score in the tail is going to have to be a 0.0668. So hopefully that's some helpful review, and for the concepts we've covered, you have a good understanding of what we've done so far, with the idea that we'll build on those further for some of the even more fun things to do with statistics that we're trying to build up to. So looking to hear your thoughts, and perspectives on what's working, what makes sense, what other ways could you see applying this coverage of probability in the future. We'll talk to you next time.